Hello, in this video we are continuing our discussion of section 8.6 on finding power series for functions, finding new power series for functions. And in this lecture we are concentrating on finding new power series by using either integration or differentiation. So in example 3 we are going to use the power series from example 1 part C. So this is what we found in the previous lecture on this section, that 1 over 2 plus x, that function is equal to the sum from k equals 0 to infinity of negative 1 to the k, x to the k over 2 to the k plus 1. And this is true for the interval of convergence where the absolute value of x is less than 2. So we're going to find a power series representation for 1 over 2 plus x squared, and we're going to find the complete interval of convergence for this new power series representation. So this is a little bit different from the previous example because that example only asks us to find the radius of convergence. So we're going to find the complete interval of convergence, and we'll see what the difference is there when we get to it. But first we're going to find a power series representation for 1 over 2 plus x squared. So we need to compare 1 over 2 plus x squared and 1 over 2 plus x. Since we have a power series for 1 over 2 plus x, basically we need to think about what do we do to 1 over 2 plus x to get 1 over 2 plus x quantity squared. And this do is those 5 options that we talked about in the previous example. So the first one is a sum or a difference. The second one is multiply by a power of x. The third one is substitute. Oops. There we go, substitute. In a function for x. The fourth one is differentiation. And the last one is integration. Now, as I already said, in this lecture we are concentrating on differentiation and integration. But in general, you would need to go through a checklist. So see if we can add or subtract 2 functions together to get the new function that we need. Well, that's not the case because we've only been given one function, so it's not that option. Multiplying by a power of x. No, we don't just multiply by a power of x in order to get this new function. Substituting in a function for x. That would mean changing just this one term. And possibly simplifying a little, but that's not what we have. We have the entire denominator being squared. And really, this is substituting in a power of x. Okay, so not any function, but a power of x. Multiply by a power of x or substitute in power of x. So then we have gotten to differentiation or integration. So the question would be, do we differentiate 1 over 2 plus x to get 1 over 2 plus x squared, or do we integrate it? And in this case, it is differentiation. So let's notice that the derivative with respect to x of 1 over 2 plus x, we would write that as 2 plus x to the negative 1. So when we differentiate, we get negative 2 plus x to the negative 2. Derivative of the inside is 1, so we just have negative 1 over 2 plus x squared. So we want to come up with a power series for this. We need to account for that. The way that we're going to do that is by changing the sign for both. So this means that 1 over 2 plus x quantity squared is equal to negative derivative with respect to x of 1 over 2 plus x. Now we have a power series for 1 over 2 plus x, so we're going to substitute that in. And this is the sum from k equals 0 to infinity of, let's see, negative 1 to the k, x to the k over 2 to the k plus 1. So again, we are going to differentiate term by term, just like what we saw with the integration. We can split a sum with a derivative, so that means we can take this derivative and pull it inside of the sum. So we have the sum from k equals 0 to infinity of the derivative with respect to x of negative 1 to the k, x to the k over 2 to the k plus 1. Negative 1 to the k and 2 to the k plus 1 are constant, so those can both be pulled out of the derivative. So we have negative sum from k equals 0 to infinity of negative 1 to the k over 2 to the k plus 1 times the derivative with respect to x of x to the k. And now this has reduced to simply differentiating x raised to a power. So we get negative sum from k equals 0 to infinity of negative 1 to the k over 2 to the k plus 1. The derivative of that, we're going to bring our power down and subtract 1 from the power. So we get this. And one thing you can notice here, when k is equal to 0, the term k times x to the k minus 1 is equal to 0 times x to the negative 1, which is really just 0. Now we prefer not to have x being raised to negative powers, even if it's multiplied by 0. So what we're going to do is, because of the fact that that term goes to 0, we're going to throw out when k is equal to 0. So we end up getting, really shouldn't have written k equals 0 here, because we are instead going to say that the sum starts at k equals 1. So negative sum from k equals 1 to infinity of negative 1 to the k over 2 to the k plus 1 times k x to the k minus 1. Okay, so this is the series that we get here. So 1 over 2 plus x squared is going to equal negative sum from k equals 1 to infinity of negative 1 to the k times x to the k minus 1 over 2 to the k plus 1. So here is our function and our power series representation. But the problem also asks us to find the interval of convergence. Well, to find the interval of convergence, we know that the radius of convergence stays the same. The original series converged for absolute value of x less than 2. So this means that r is equal to 2. So this is still our radius of convergence. Also, the center for our series, if we go up to our series here, we're going to take our x to the k minus 1 and set it equal to 0. So that x term, set it equal to 0, ends up meaning that our center is 0. So the interval of convergence contains the interval where the center plus the radius and the center minus the radius. So that is equal to 0 minus 2, 0 plus 2, which is the interval from negative 2 to 2. So this is most of the interval, but it's not all of the interval because we need to check the endpoints. Remember, the theorem in this section involving differentiation and integration only guarantees that we have the same radius. It doesn't say anything about the endpoints. So we do need to check those individually. So, starting off with x equaling negative 2. We have the sum from k equals 1 to infinity, well, negative of that, although that's not going to change our convergence or not. Then we have -1 to the k times x to the k minus 1 over 2 to the k plus 1. So we're going to substitute -2 in for x, so we get the sum from k equals 1, negative sum from k equals 1 to infinity. One thing we can do, so there's a little bit less to write, notice we can take this -1 and combine it with the negative here and add 1 to the power. So I'm going to go ahead and do that over here so that we get -1 to the k plus 1. Then we'll have times k times -2 to the k plus 1. Nope, that should be a k minus 1, sorry. All over 2 to the k plus 1. Now the way that we are going to figure out whether this converges or not is we first need to simplify it. So if you notice, we have 2 raised to a kth power, -1 raised to a kth power, and a -2 raised to something. So we need to figure out how all of these things combine. The best way to do that would be to write this -2 to the k minus 1 as a -1 times 2 to the k minus 1, which is equal to -1 to the k minus 1 times 2 to the k minus 1. So then we're going to have a -1 to the k plus 1 times -1 to the k minus 1, which if we add our powers there, since we have the same base, this is going to give us a -1 to the 2k, and notice that 2k is always an even value. -1 raised to an even value is going to be +1, so that just simplifies to 1. And we have a 2 to the k minus 1 divided by a 2 to the k plus 1. Now, since we have the same base but we're subtracting, we will we're dividing, we will subtract our exponents. So we end up with 2 to the -2, or 1/4. So this means that we have the sum from k equals 1 to infinity of our negative signs all end up canceling out, just gives us a 1. We have this k here. The negatives, or the 2's, end up giving us just a 1/4. So we have something that looks like k over 4. So the sum from k equals 1 to infinity of k over 4. And this is the series that we get when x is equal to -2. So now we need to think about the different series tests that we have. The easiest one to apply here is going to be the divergence test, or the test for divergence. So if we look at the limit as k goes to infinity of the kth term, that's going to be the limit as k goes to infinity of k over 4, which is going to be infinite, which is definitely not equal to 0. So this means then that the series diverges. Because the series diverges, it means that we are not going to include it in the interval of convergence. Okay, so that's one of our endpoints. The other endpoint, when x is equal to 2, we're going to do a similar process. When we plug it into our series, we'll have the sum from k equals 1 to infinity of -1 to the k plus 1 times k times 2 to the k minus 1 all over 2 to the k plus 1. There's a lot of stuff that simplifies similarly here because the only difference is we have a +2 instead of a -2. So that means that we're not going to have anything affecting our -1 raised to a power. So we'll have the sum from k equals 1 to infinity of -1 to the k plus 1 and a k. The 2's still combine in exactly the same way as what we saw up here, so that we end up with a 1/4. So we have k over 4. Now this is an alternating series. We could actually apply the test for divergence here as well, because if we look at the limit as k approaches infinity of k over 4, since this equals infinity, this means that the limit as k approaches infinity of -1 to the k plus 1 times k over 4 is not going to exist. And if it doesn't exist, it definitely doesn't equal 0, which means that this series diverges. And again, we won't include it in our interval of convergence. So this means that our interval of convergence is the interval from -2 to 2, not including either one of the endpoints. So our final answer then, we have our function, 1 over 2 plus x squared. We have our power series, so this is a sum from k equals 1 to infinity of -1 to the k plus 1 times k times x to the k minus 1. Sorry about that. K minus 1 all over 2 to the k plus 1, and this is true for -2 less than x less than 2. And there is our final answer for example 3.